Hi, in this video, I will present our paper on the decidability of reachability in continuous time linear time-invariant systems. This is joint work with Mohan Dantam. Let me motivate the problem with a simple example coming from physics, where we attach a mass m to the ceiling by a spring k and a damper b. We denote by z the distance between the ceiling and the mass, and we apply some external force u to the system. We can write the equation of motion by using Newton's second law, and we obtain a second-order affine differential equation. This equation is not of the first order, but by introducing more variables, namely the derivative of z and the constant function y, we can turn it into a system of differential equation of the first order. More precisely, the system we obtain is of the form x prime equals ax plus u. Such systems are known as linear time-invariant systems. Naturally, in general, we'll have some constraints on u, but we'll go back to that point later. More generally, linear dynamical systems, either in the discrete case or the continuous case, appear everywhere, such as in biology, software verification, probabilistic model checking, combinatorics, electrical circuits, and many more. Typical questions include reachability, safety, and when we add a control to the system, controllability. There are many more questions, such as optimal control, feedback control, stability, and so on, but I will not talk about them in this presentation. Let me go back to a very simple example of a simplified one-dimensional car, in which we only control the acceleration of the car. This means we control the second derivative x of the position of the car. Initially, the car is at position A with no speed, and our goal is to reach position B also with no speed. The question is, what kind of control U should we use so that the car goes from position A to position B? One possible solution is simply to accelerate until the car reaches the midpoint between A and B, at which point we brake as much as possible and we stop exactly at position B. This means the control will be piecewise constant. The acceleration will linearly increase and then linearly decrease, leading to a nice smooth second-order curve. But this is not the only solution. In fact, in reality, the car probably cannot withstand an arbitrary acceleration, and there are speed limits on the road, which means a more realistic solution will look like this. We will first accelerate until we reach a cruising speed v. At this point, we will wait until at the end only we will brake and stop exactly at position B. If we rephrase this problem mathematically, we see that the problem is how to go from position A0, A being x and 0 being the speed, to position B0 being the position and 0 being the speed. In other words, this is a point-to-point reachability problem in dimension 2. The problem we're interested in is what we call the LTI reachability problem, where we're given a source, that would be the initial position of the car, the target position, which would be the final position of the car, the transition matrix A that describes the physics of the system, and a set of controls U. For now, U can be any set in Rn. The question is there a finite time t and a measurable control U, such that if we plug U into the differential equation x prime equals ax plus u, the solution starts from position y and ends at position z at time t. The only condition on u is that u be measurable so that the equation makes sense. This is very important to note that the problem is a decision problem. We're only asking whether it is possible to find such a u. We do not need to describe u. In fact, if we ask u to be describable, for example, by a piecewise polynomial, this is an interesting problem, but it completely changes its nature. In this talk, we will only be interested in whether such a solution exists or not. We can see this problem as a special case of a more general continuous reachability problem, where we're trying to go from a source y to a target z by using a set of controls, but the transition function f can be an arbitrary function of time, the position x, and the control u. In particular, notice that the system is now time varying because f can depend on t, and t can be nonlinear. This problem is generally undecidable. For example, for nonlinear systems, even without control, the point-to-point reachability problem is known to be undecidable. even when the derivative of f is piecewise constant and is still without control, the point-to-point reachability problem is also undecidable. And in the case of discrete systems, a very particular class of linear systems that are called saturated again is undecidable without control. This means that LTI systems probably form the most useful class that is not straight undecidable because of the above results. But as we will see in this talk, it's not actually clear that a point-to-point reachability problem for LTI is so easy to solve. Going back to the LTI reachability problem, there is a lot of work in the literature about variants of this problem, the most common one being the global no controllability problem, where the question is whether we can reach all points in Rn starting from the origin. We can also ask whether every point is reachable asymptotically, which means when time goes to infinity, but some points may not be reachable in finite time. Another question is whether we can control to all points around the origin in an open neighborhood. This is a more local version of the problem. A very important question, especially for nonlinear systems, is that of stability. That is, whether the trajectory remains bounded when u is bounded. And finally, a very important practical problem is to approximate the set of reachable points from y in an efficient way. But in this talk, we'll only be interested in the exact point-to-point reachability problem. Furthermore, we can make plenty of assumptions to simplify the problem. Generally, we'll make spectral assumptions on A, such as A being stable. We'll also make assumptions on U, as we will see in the coming slides. Finally, as we saw before, we can also make restrictions on the acceptable set of controls U, such as being piecewise polynomial. This means that there are lots of problems to look at, and indeed, the literature on the problem is very exhaustive. Let me have a look at two extreme cases that are known to be solvable. The first case is when there is no control, that is, U is the set containing only 0. In that case, the solution to the differential equation has a closed form that involves the exponential of a matrix. It was shown in 2008 that the question of whether given y and z and a matrix A, there exists a time t such that z is the exponential of at times y is decidable. In fact, it was later shown that it is decidable in polynomial time. However, let me point out that this theorem is not trivial at all to prove. Another textbook example is when the set of controls U is a linear subspace that is described by a matrix B. In that case, it is not very hard to see that the solution to the system x prime equals ax plus u must always live in the span of the column of B of AB, a squared B, and so on. In fact, it is a simple exercise to show that the converse is also true. In other words, a point is reachable if and only if it belongs to this linear subspace, and therefore the problem is easily decidable. However, going back to the example of the car, remember that in practice, the acceleration and the braking power of a car is not arbitrary. In fact, it is very much finite, which means that U will be bounded. This means that this very simple one-dimensional example of a car does not fit into any of the two theorems I've stated before. In fact, there are very few decidability results in the literature about the point-to-point reachability problem. The problem we looked at in our paper is the LTI zonotope null reachability problem, in which we made two simplifying assumptions. The first one is that U is what is called a zonotope. This means that starting from a hypercube -1, 1 to the m, we apply a linear transformation B. In other words, we have m independent controls, and the matrix B describes how each controls act on the system. The second simplifying assumption is that x0 is 0. In other words, we're starting from the origin. We're able to show that the problem is unconditionally decidable in some very restricted cases. Namely, if A is real diagonal and B is a column with at most two non-zero entries. We can also decide the problem when A is real diagonalizable and all its eigenvalues are either rational or a rational multiple of the same algebraic number alpha. When A only has one eigenvalue which is real and B is a column, we can also decide the problem. And finally, in dimension 2, we can handle a case where B is a column and A has a real eigenvalue. As you can see, Those are very restricted conditions. In fact, the problem turned out to be surprisingly hard to solve exactly. In order to go further, we had to make some assumption. It turns out that reachability in linear systems often involves some number-theoretic problems. The one we'll be interested in is called Chanion's conjecture. It is a deep conjecture in transcendental number theory. It is widely believed to be true and totally open. I do not have the time to go into the details of this conjecture. However, let me explain how it comes into play. By a famous result of Wilkie and McIntyre, we know that if Chanion's conjecture is true, then for every k, the first-order theory of the reals, together with the exponential function and the cosine and sine function over a finite interval that depends on k, is decidable. If you do not know the first-order theory of the reals, it simply means that if we're given a sentence using the existential and universal quantifier, real variables, plus multiplication, the order, exponential, and cosine and sine over a bounded interval, we can decide whether such a sentence is true or not. It turns out that this theorem is extremely powerful because it allows us to show that the problem is decidable in many more cases, namely when A has real eigenvalues, in dimension 2 in all cases, and finally in the very important special case where we bound the time to reachability. This, of course, assumes that Chanion's conjecture is true. However, let me say that we do not need to know the solution to Chanion's conjecture in order to write the algorithm. Only the determination proof of the algorithm relies on the conjecture. The previous slide suggests this problem is very hard, but to show this, we had to generalize the problem a little bit by trying to reach a set z from the origin instead of a point. In this case, it turns out the problem is trivially hard in the case with no controls and z being a hyperplane. This is because of a known problem known as the continuous column problem. This problem asks whether the orbit of a linear dynamical system given by exponential atx0 intersect a hyperplane whose normal in C. This problem is known to be very hard in a mathematical sense, meaning that if you can solve it, you will probably solve some difficult mathematical question. However, it is not known to be either decidable or undecidable. In fact, proving so is probably a major open problem in this area. However, in some sense, taking the set of controls u to be equal to 0 is cheating. In particular, the reachable set is always closed, or a closed set minus the origin. However, in contrast, where we take u to be equal to a zonotope, we can show that the reachable set is always open. In other words, it will look like this diamond shape, but the boundary will not be included. From a topological perspective, those two problems are very different. In fact, it is much harder to decide membership into a closed set than in an open set in general. This is why we want to prevent this, and we looked at the LTI zonotope null set reachability problem, where the set of controls is again a zonotope and we're trying to reach the set Z from the origin. We're able to show that this problem is hard, again in a mathematical sense, by reducing from the continuous non-tangential Scaling problem. In fact, we only need a single input, and we can assume that the matrix A is stable. Z can be chosen to be either a hyperplane or a convex compact set in dimension n-1. The non-tangential version of the continuous Scaling problem asks whether the orbit of a linear dynamical system crosses a hyperplane. Notice that we're asking for the derivative to be non-zero. In other words, we cannot just touch the hyperplane and go away. Although there is no formal reduction between the two problems, we can show that this problem is essentially as hard as the continuous Scaling problem. Let me now look at the mathematics of the problem. If we're given a system of differential equation, x prime equals ax plus bu, we can obtain a closed form expression for this involving the orbit of a dynamical system and an integral. However, this formula is very hard to work with in general. In a particular case where x0 is the origin and u is the zonotope, we define the reachable set to be the set of all points we can reach by using a control from the origin. It will typically look like this diamond shape. More precisely, we know that it is an open, strictly convex set. This means the boundary is not included, and if you draw a line between any two distinct points on the boundary, all points are inside the set except for the 2 points on the boundary. Furthermore, we can decompose the reachable set. if we denote by B1 up to Bm the columns of B, and U is a hypercube, the reachable set will be the Minkowski sum of some smaller reachability problems that involve the columns of B. This is why we focus in the case where B is just a single column. In this case, there is an explicit formula for the boundary of the reachable set that again involves an integral and a sine function. It is not immediately useful at first to look at this formula. However, as we will see, this is what we use to conclude in some cases. First, let me say that if the target Z is not on the boundary of the reachable set, deciding whether Z is reachable is trivially decidable, because we can always approximate with arbitrary precision both the reachable set and the non-reachable set. Therefore, one of the two algorithms will eventually terminate. This is why we only focus on deciding membership into the boundary. If we look at the formula for the boundary of the reachable set, and we denote by fc the function that appears in the sine function in the integral, we notice that this function looks very much like a continuous column problem. In fact, the question is whether there exists a time t such that fc of t is 0 is exactly the continuous column problem. In other words, the question whether the sign of that function is constant is a very hard problem. Furthermore, even if we could somehow solve the continuous column problem, it would not necessarily help compute the border, because it will only tell us if the sine function is constant or not, but not help us compute the integral. This looks like this problem is indeed very hard. However, in some good cases, we can show that the zeros of the function fc can be described in the first order theory of the reals. In this case, we obtain unconditional decidability. In some less good cases, we can show how to describe the zeros of fc in the first order theory of the reals together with the exponential function. In this case, we rely on Chanel's conjecture to obtain decidability. Finally, in all the cases we are stuck because the zeros of fc will generally involve the sine and cosine function over unbounded domain. Unfortunately, the first order theory of the reals together with the unbounded sign is undecidable because we can encode the integers. In the remaining time, rather than explain the proof, I will simply explain two examples that will illustrate the technique we use in the paper. The first example is probably the simplest example I can imagine. We're looking at a two-dimensional system where the matrix A is diagonal with negative eigenvalues that are rational. The matrix B has two columns, B1 and B2, that are symmetric. By the decomposition result that I mentioned before, this diamond shape is in fact the Minkowski sum of two smaller reachable sets that are symmetric with each other. This means that we only look at the case of B1. By using the formula from the previous slide, we can explicitly write down the formula for the boundary, which will involve an exponential and the integral as well as a sine function. If we look at the formula inside the sine function and we solve for 0, we find that the only possible solution is t equals to 6 times the log of the ratio between C1 and C2. At least we have an explicit formula, but this is not a nice number because we cannot write it down in the first order theory of the reals. However, it turns out that if we plug t into the equation and we introduce a real number alpha that is the ratio between C1 and C2, we can simplify the result and write it only using polynomial equations. In other words, all the complexity disappeared and we can write the equation in the first order theory of the reals. We can obtain a parametric equation for the boundary, and hence deciding membership of a point PQ in the boundary is exactly deciding the following formula. While this formula involves an absolute value and a sine function, it is not very hard to see that it's still expressible in the first order theory of the reals, and therefore the problem is decidable. Let me now modify the example a little bit by introducing an irrational eigenvalue in A. The picture will look exactly the same, but the math will be quite different because of this number square root of 2. By using the same argument, we can again obtain a parametric equation for the boundary. However, notice that this time there is a difficulty because we need to raise the absolute value of t to the power of square root of 2. In other words, this is not a polynomial anymore. This means that deciding membership of a point PQ in the boundary will now involve some non-polynomial equations, and we can only write them down using the exponential function. In other words, this is expressible in the first order theory of the reals with exponential, but not in the first order theory of the reals. However, In this case, we can still show decidability by noticing that the first equation implies, up to a sign, that p raised to the power of square root of 2 is equal to q. However, in practice, p and q must be algebraic numbers in order for them to be describable to the computer. It turns out that if p is algebraic, then p over 2 raised to the square root of 2 must be a transcendental number by a Gelfand-Schneider theorem, and hence q cannot be algebraic, which is a contradiction. In other words, the boundary of this reachable set does not contain any pair of algebraic numbers, and therefore the problem is decidable by the argument that I've said before. That is, the problem is decidable if the target point is not on the boundary. Let me say a few words about the hardness. Remember that the formula for the boundary is an integral that involves the sign of a function fc. If fc is a strictly positive function, its sign will be constant equal to 1, and this integral is easily calculated. In this case, beta of c is equal to a minus 1b, but it is in a boundary, therefore not reachable. In other words, the picture will look like this. Notice now that if fc is allowed to have some tangential zeros, this property is still true because the zeros of fc are at bounded distance from each other, and therefore they do not change the value of the integral. If fc has some non-tangential zeros, by continuity, it will be negative for a non-trivial amount of time. This can be used to show that the scalar product between c and beta of c will be strictly smaller than the scalar product between c and a minus 1b. In other words, the point a minus 1b will not be in the reachable set, but it will not be the furthest point in direction c compared to the rest of the reachable set. To put it differently, if we take a line c going through the point a minus 1b and that is perpendicular to direction c, in the first case this line will just barely touch the reachable set exactly in point a minus 1b. However, in the second case, this line will intersect the interior of the reachable set. In other words, we can distinguish those two situations by checking whether the reachable set intersects a hyperplane. To conclude, in this paper we looked at the LTI reachability problem where the set of controls U is assumed to be a zonotope. This problem occurs very naturally in the control theory, and surprisingly, the point-to-point reachability problem has not been studied a lot in the literature. We are able to show that the problem is decidable in dimension 2 or with some very strong spectral assumptions. It is also conditionally decidable with real eigenvalues or in bounded time. Here, we require that some mathematical conjecture, known as Chanio's conjecture, be true for our results to hold. And finally, we were able to show that the point-to-set reachability problem, again with a zonotope, is at least as hard as the non-tangential continuous Gaussian problem. This suggests that the problem is indeed very hard to solve. Thank you.